I resumed recording, and we're back again. And I want to go through the lecture material together for analysis of variance. You're going to see a lot of similarities between what you saw in the actual real calculation of the analysis of variance. You'll see a lot of that repeated here, but you'll also see some of the basis for it, some of the assumptions that are involved, and so on and so forth. So it's important to know that as well. So what I'm going to do is I'm going to go through this PowerPoint, but I'm not going to play it full screen as a regular PowerPoint. If I play it full screen, I won't be able to see your comments or responses to my questions, since I won't have my control panel available that has a chat box on it. So I'm going to just step through these slides the way that they are here. Okay, for starters, what are we looking to demonstrate here? Okay, so we want to understand this idea of analysis of variance that involves this one single factor, this one single variable that we take the means that we're calculating, that one numerical variable. Okay, we want to be able to understand what the assumptions are, and there are some assumptions that we have to meet when we do this, and we've seen this before for the t-tests, independent samples and so on and so forth, and random samples. So there's going to be similar kinds of assumptions that we're going to want to comply with. We're going to want to know how to interpret, how to run the test. We already looked at it using Excel and SPSS, and we're going to, particularly with SPSS, which is really the way we're going to be likely using this in the future, we're going to want to understand how to interpret that ANOVA table. We started to go through that. We actually started to identify what each number represented that ANOVA table. So that's why it was so valuable to do that initial Excel exercise, so you can see where those numbers wound up in that table. And then we want to see when we're permitted to carry out these post hoc tests, and how we can interpret the post hoc tests. Okay, so let's take a look at this. So when we were working with the t-test, we typically were looking at two groups. Okay, for instance, in this particular data set, we're looking at response time from a cell phone for some, I guess, an emergent for data or something like that, and response from some other control, whether it's voice and data or cell phone, just cell phone voice only, and so on and so forth, with the response time different onto them. So apparently what they did was they took many samples in each of these two conditions, where they were working with cell phone and with voice only, or data with voice and data, and so on and so forth. And they found so they took many readings and so on and so forth for each of these two groups. And then they looked at the means. They compared the means of these two groups. Now, this is one way to describe the null hypothesis, right? We've gotten used to using mu1 is equal to mu2. In other words, the mean for group 1 is equal to the mean for group 2. But you could just as easily describe it as the mean for group 1 minus the mean to group 2 is equal to 0. In other words, there's no difference between them. They're equal. Or the mean for these two groups are not equal to 0. In other words, there is a difference. Now, just to remind ourselves, this is known as a two-way t-test. Okay, now there are one-way t-tests and there are two-way t-tests. The reason why this is a two-way t-test is because we do not assume that that when we reject the null hypothesis, or in our plan to reject the null hypothesis, we don't pre-assume whether or not the difference in the mean means group 1 is greater than group 2 or group 2 is greater than group 1. We're just looking to demonstrate that the two means are different. We're not assuming that that one is greater than the other. And that would be phrased a little bit differently. Okay, in other words, if we wanted to prove that group 2 is greater than group 1, we would say that the alternative hypothesis is mu1 is greater than mu2. And that would make our null hypothesis that mu1 is equal to or less than mu2. So there's still the equal sign in here, but now it's got a little bit more of a complication. That would be a single-sided t-test. Okay, this is a two-sided t-test. mu1 is equal to mu2, and mu1 is not equal to mu2. That's a two-sided t-test. The result could go either way, doesn't matter. We're just looking for a difference. Put that aside for now. Later on, we'll bring that up before we get to the second exam, and maybe in review, I'll bring that up and describe it to you. I won't try and trip you up on that. I want you to see it and understand it, but I'm not sure that we'll wind up with a problem on the exam that involves that. I might add something to the homework that'll give you a chance to exercise that idea. Okay, so let's take a look at this. Well, now, let's say we were evaluating training programs, except that now, instead of there being two groups that we want to compare the mean of, there are now three groups that we want to compare the mean of. Well, when we had two groups, we could see we could compare box plots. We could see the variability between the two groups. We could test using the t-test for the difference between the groups, see if there is a difference in the means. Well, now we have three groups. That complicates things a little bit. We have observations for three groups. In this example, we have three observations, a small data set. We have three observations for each of the three different learning methods. In this case, it's the amount of time it takes to learn a task using method one. Three people, randomly selected people, attempted to learn the task using method one, then another three using method two, and another three randomly selected people used method three, and that's the amount of times that it took to learn it. So it looks like that it took a bit longer than to use method three to learn the task than the others. Okay, but we're prejudging that a little bit. So let's go further with this. Okay, so one of the things we can do to start out with, and we've done this with the t-test, where instead of just going in and doing the t-test, I've gone to the descriptive statistics and I calculated the mean and the variability for the groups that we're comparing. In the case of the t-test, the two groups. In this case, we went to the descriptive statistics for the three groups. And as it turns out here, sample size is 3. The smallest value is 9. The biggest value is 16 for method 1, as we saw before, right? That's literally what we have here, 9 and 16, smallest value. The average of the three readings for method 1 is 12 minutes. And the standard deviation, just calculated the way we would normally calculate standard deviation, except for a sample of size 3, is equal to 3.6. And then we went to method 2, and again, group size is 3, and we found the mean was 13, and the variability, the standard deviation, was 2.6. Finally, method 3 is 18 with a variability of 3.8. You know, the variability of these three groups is not very different, right? So the variability is pretty similar. But look, the means are quite different, particularly for method 3. So I'm beginning to suspect that maybe method 3 is genuinely, for if we applied it to the entire population, that method 3 would demonstrate that we'd be able to demonstrate that method 3, the mean for the entire population using method 3, is going to be different than it is for method 1 and 2. And why am I thinking that? Because I'm thinking the variability is not that great, but the difference between method 3 and these other two means is pretty large. So gee, I'm encouraged by looking at these descriptive statistics. Does this prove anything so far? No. It doesn't really prove to us that we're sure that the population differences are different, right? So let's move on to another way of displaying this information. So here are side-by-side box plots for the same information. This is group 3, group 1, this is method 1, method 2, and method 3. And we can see that there isn't much difference in the median values for the method 1 and 2. And the variable, there's quite a bit of overlap between the data, but method 3 is quite different. There's very little overlap or no overlap for the three values. And you'd almost be tempted to say, well, you know, there's no overlap here between these other two. Can't I just say that this must be different than the means for these other two groups? Well, it's tempting to say that, but you have to remember that this box plot only represents the sample, not the entire population, especially with a small sample like 3. Maybe it's not that representative of the entire sample. And in fact, the variability is much larger for the entire group of people that learn this task, right? So we really can't make that assumption without demonstrating that the probability that we would be wrong if we were going to go that direction is going to be less than 5%. So this is interesting. Just like we got a good look at the differences in the means and the amount of variability, and it was encouraging. And these spots plots are encouraging. And it seems like we should be able to demonstrate a difference between method 3 and these other two methods. Maybe not between these two methods, given how little data that there is, but maybe we have a shot at method 3, right? So it's encouraging for us to go a bit forward. Okay, so if we were to use the t-test here, how would we have to do this? Well, we'd have to compare method 1 to method 2, then method 1 to method 3, and then method 2 to method 3. So we would have to run the t-test 3 times. Each time we run the t-test, we have a 5% chance of a type 1 error, an error that we always want to avoid type 1 errors because very frequently type 1 errors are going to make you go to expend money or effort or take risks or do some sort of intervention on the belief that there's a difference between whether or not you do that intervention or not and what the outcome might be. So we don't want to encourage an intervention, taking a drug that we've tested, and so on and so forth, and taking risks associated with that, unless there is a suitable level of chance that we would be right. In other words, we want to make sure that we don't make that error more than 5% of the time. That's our alpha error. Okay, so we want. Oops, we go back here. Okay, so we want to find a method of comparing these means that'll do it in a single test with a 5% risk of a type 1 error overall. Okay, and that's what our analysis of variance is for. It's going to allow us to compare these 3 means without repeatedly doing the t-test and increasing our level of error. Could we do it using the t-test? Yes, we could, but then our chance of being wrong and creating a type 1 error or an alpha error would be increased. Okay, so we want to compare the differences in the three means for group 1, group 2, and group 3. Okay, so as I mentioned before, the probability that you would be right if you reject the null hypothesis, if you succeed and get a result less than 0.05, would be 95%. In other words, you're 95% confident that your outcome is correct when you reject the null hypothesis. If your p-value is less than 5%, you're 95% sure you're right. Well, if you do that 3 times, and each time you're only 95% sure you're right, then the probability that you would be right is going to be 0.95 times 0.95 times 0.95. If you work that out, it's going to come out to 86%. So by repeatedly applying the t-test to these three samples, your probability that you would be right when you reject the null hypothesis goes from 95% to 84%. In other words, it increases your probability of being wrong from 5% to 14%. Okay, that's basically what this has done. It's taken our 1 minus 0.05, which is 95%, and subtracted 1 from it, which leaves 5%, and it's actually tripled, cubed. They multiply this level of error to 0.95 times 0.95 times 0.95 and subtract it from 1, and this is your new level of error. Instead of alpha's 0.05, now if we do it that way, it's going to be 0.14, which is not tolerable. Okay, so basic idea of analysis of variance. We've seen this. If we can demonstrate that the means are far apart, but the variability within the groups is small, it's easier to demonstrate that these means are different than it is to demonstrate that these means are different. Even though if you look across, the medians are exactly the same for each of these three. Because of the increase of variability within each group, it's going to be harder for us to prove that they're different here with this extra variability within the groups as opposed to this situation where the variability between the groups is small. Okay, this is what it looks like if you looked at it from the perspective of our distribution of the possible populations or sample distributions. Okay, this one, the group 3, which was the largest number, the largest mean, right? If they all have the same variability, which they kind of have if you look in this picture, right? The spread on these 3 distributions is very similar. Okay, but we can see that mu3 is much different, say, than group 1, the mean for group 1. And in fact, that the overlap between these, this area between them, where if we get a sample result, it could be from either one of these 2 groups, this area becomes smaller and smaller. And if this area here is less than 5%, we can reject the null hypothesis that mu1 is equal to mu3. Right, so that's really what we're looking for, is that the probability that we would get a sample outcome that would be could be from more than one of these groups, or we want to reduce that probability to less than 5% in order to reject the null hypothesis. Okay, so reminder, we designate population parameters, the mean of the population for each of the different groups, and the standard deviation of each of the 3 populations. We distinguish them by using Greek letters. So this is the mean, this sigma, mu, and this is the standard deviation for the populations. We very rarely ever actually have that information, in fact, almost never, right? So we are going to work with the statistics from which is the results of samples from each of these 3 groups. Okay, in that case, it's going to be X bar 1 and X bar 2, etc., all the way up to the last group, right? And the standard deviation is going to be standard deviations of the values within each one of these groups. The standard deviation of group 1 and standard deviation of group 2 and 3 and 4, all the way up to the number of groups that we're working with. Okay, so what are our null and alternative hypotheses? Okay, well, when we were doing the t-test, going back to the t-test, okay, when we were doing a t-test, if we did a single sample t-test, our null hypothesis was that the mean of the population that we're examining, that we're sampling, is equal to a known mean, mu0. Sometimes we would see that as the mean, mu, is equal to the value that is, like mu is equal to 30, or mu is equal to 40. And our alternative hypothesis was that mu is not equal to that value. That's a situation where we have a value and we have a single sample that we take from a population, and we want to compare our mean to that value. When we go to do a 2-sample t-test, right? Well, in that case, we have 2 samples, so we want to compare. Our null hypothesis is that mu1, mu for the first group, first population, is equal to mu for the second population. Notice all our hypotheses always use mu. They never use X bar, because we may be working with X bar and we may be working with standard deviation to demonstrate this, but it's always, our objective is always to prove that the means of the populations are different, not the means of the samples. We already know what the means of the samples are and whether they're the same or different. We need to use that to prove that there's a difference between the means. So for 2 populations, 2 groups in our categorical variable, mu1 is equal to mu2, and alternative is mu1 is not equal to mu2. Again, 2-sided, right? Because it doesn't matter whether the mu2 is less than or greater than mu1. Finally, we run into the situation where there might be more than 2 groups. So our null hypothesis for that is going to be mu1 is equal to mu2 is equal to mu3 is equal to mu4, up to mu for the total number of groups that we have. G could be 3 for this situation, could be 5 if we had 5 different possibilities. Okay, and our alternative hypothesis is not mu1 does not equal to, is not equal to, is not equal to, is not equal to, because we can't demonstrate that without doing repeated t-tests, right? Our alternative hypothesis is that not all the population means are the same, okay? Or you could phrase that another way, at least two population means are different from one another, okay? That's different from the way we would phrase our alternative hypothesis for when we're dealing with two populations. Okay, any questions so far? Just want to make sure you're still awake. I know this is why I don't like doing PowerPoints, because PowerPoints are sleep inducing. Okay, good. All right, good. Thank you. Okay, so let's do some more sleep. We'll continue with this. Okay, so what are our assumptions here? Okay, so now one of our assumptions is that the populations that these samples are drawn from are normally distributed. Just like the t-test. The t-test, one of our assumptions is that it's drawn from an approximately or a normally distributed population. Well, remember the central limit theorem? We learned about samples, and we learned that, you know, even if the population is not normally distributed, if it's skewed, for instance, right? If we took large enough samples and did repeated those large samples, that the distribution of the sample means would be normally distributed. So we could actually modify that rule a little bit. We could assume one of the assumptions that we have is that the data, the actual material, the actual populations are normally distributed, or that we have a large sample size. So we can apply the central limit theorem and say, oh, even though this is not so, maybe not completely true, then, but we can still trust that our samples are normally distributed. Sample results will be normally distributed if we repeat them. So we can look past some skewing or issues with the distributions. Okay, so it's either the normal distribution, the population distribution is normally distributed, or the sample size is long enough. Okay, and analysis of variance is a robust and conservative. In other words, we can tolerate some deviation from being normally distributed, right? So some statistical analysis, you may not be able to tolerate it, but for analysis of variance, you can. One way analysis group is generally safe when, okay, if we're working with three groups, if the total sample size of the three groups is greater than 15, and there are no outliers. If the sample size is between 15 and 40, and the data or the population only moderately skewed, and there are no more than three outliers, or if the sample size is greater than 40, then we can tolerate even a bit of skewed data and even some outliers as well. Okay, so that's bigger sample sizes, the more robust and the more confident we can be in the results of the analysis of variance. Okay. Okay. Homoscedasticity. Okay. What that word means is equal standard deviations. That's another one of our assumptions, that the standard deviations, the variability of these groups are equal, that they're the same. And again, they don't have to be perfectly the same. In fact, there are some statistical tests that we can run that'll help us determine whether they are can be assumed to be close enough to being equal to use analysis of variance. But for the most part, when we're looking at the data, when we take our descriptive statistics and we just look at the data, if the standard deviations don't differ by a factor of two, in other words, one is not double what the others are, then as a rule of thumb, you can assume that this assumption of homoscedasticity, equal standard deviations, is not violated. Okay, and then of course we want our samples to be random and independent, as we do in many of them. So these are our assumptions for analysis of variance. So if I were to ask you on the test, what are the assumptions for analysis of variance? Or which of the following, check off which of the following boxes for which of the assumptions for the analysis of variance. You could go through there and in fact you would know, come right back here to this, you'll be doing it with their open book tests. You'll be able to come back to this point in this PowerPoint or PDF file, which is on there also, and look up if you don't remember what the assumptions are. But to tell you the truth, the assumptions for this and the assumptions for a lot of other tests that we do have a lot of similarities. Okay, so how do we calculate the analysis of variance? Well, I won't go into this in too much detail, but basically we just saw this is the sum of squares, right, divided by the degrees of freedom basically here, right? The number, add up all the groups minus the number of add up all the values minus number of groups, and and so on. This was 2 minus 2, and this is the groups minus 1, and so on and so forth. So this would be 12, this would be 2, I guess. I forget which one is which. Between would be 2, and so on and so forth. And this would be the calculation for the variability between the means and within the groups. And then once we've done that calculation, as we've demonstrated using Excel, then we would put the average sum of squares between the groups, which is the means, right, over the average sum of squares, the variability within the groups. So you want this number on the bottom to be small and the number on top to be big, so you get a big value for the F statistic. Okay, so let's go back and through this now. If the null hypothesis is true, right? If null hypothesis is true, the F statistic has an F distribution, an F distribution, where if you look down here, you see different graphs for different sample sizes between different number of groups, different number of samples within, different number of readings within each group, and so on and so forth. But basically, if the null hypothesis is true, you would expect the F statistic to be a relatively small number, right? That the variability might be large, and the difference between the means might be small. So the difference between means is small. You might if the null hypothesis is true, then you would expect the means to be not very different, and certainly not very different that you'd be able to distinguish them given the amount of variability that there is. So if the null hypothesis is true, then we would expect the F value to be small. Okay, but that's not the way we test for it, right? We assume the null hypothesis to be true, and then we look to see if we can't demonstrate that it's not true. Okay, at least to the level of probability that one. So the analysis of variance test that we're doing for comparing the population means of several groups, we're going to examine that, calculate the F value, and then go to our table, which represents all these different, depending on what the sample size is, the number of groups. You would have a table. You would have that table and look up the F value for 5% left in the tail, what that F value has to be for each one of these different circumstances. How many groups, how many samples within each group. Okay, and once you've done that, you would look to see if your F statistic is so large that there's only a 5% chance that you would get that value, that large an F statistic, if the sample means were, if the population means that those samples came from were equal to one another. In other words, that the population means are equal to one another. Okay, so if we get that F statistic big enough so that the possibility that they're equal, those means are equal, is less than 5%, we can go ahead and reject the null hypothesis. Okay, so we want a significance level, a p-value of less than 0.05 if your presumed alpha is 5%. If I wanted to be 99% certain that I didn't create a type 1 error, right? Well, in that case, my alpha error would be 0.01, and my critical value of F would be a bigger number. It would have to come from a different table. Okay, so here we go, looking at the variability within these groups, and this is the average variability between the means and the variability within each group, and so on and so forth. Just another way of presenting it graphically. Same thing we kind of did with the box plots. Okay, now if we do this test using SPSS, which is typically how we're going to do this test, SPSS is going to produce a table. That table is going to give us the sum of squares between the groups, just as we calculated in Excel, and the sum of squares within the groups. Then it's going to take the degrees of freedom between the groups. 3 groups, there would be 2 degrees of freedom, or within the groups. In this case there are 3 groups, and this number is 6. The reason why that number is 6 is because there's 3 values in each group. There's 9 values altogether, minus 3 groups makes the degrees of freedom within the groups 6. The n minus the number of groups. Okay, and then we would take that degrees of freedom, divide it into the sum of squares to get an average of the sum of squares and the mean sum of squares, and that would be 124 in this case. And the average within the groups, divide that by 66 by 6, is going to be 11. And our F statistic is going to be the ratio of the variability between the means, between the groups, which is the variability of the means, over the variability within the groups. We want this to be a big number, this to be a small number. So when we divide this into this, we get a big number F. And in this case, we got the number 11. And we already saw what that looked like. I think our critical value was 3.89 for 3 groups. And for, I think that one though was for 15 degrees of freedom. So this might be a little bit different. But in any case, we see 11 looks like a pretty big number, given it's only 3 groups. And if we move over to the significance, we can see the probability that we would be wrong if we reject the null hypothesis that all of the means are equal to one another. Probably we'd be wrong, period, and do a type 1 error would be 0.009. So we would reject the null hypothesis whether alpha was chosen to be 5% or alpha was chosen to be 1%, whether we want to be 95% certain or 99% certain. Both cases, we would have rejected the null hypothesis, accepted the alternative hypothesis. And so that tells us at least one of the means, one of the means of one of these populations is different than the others. Okay, doesn't tell us which ones, doesn't tell if all of them are different, but it just tells us that at least 2 of the means are different from one another. They're not all equal. Okay, so SPSS, analyze, compare means, because we're really doing, even though it's analysis of variance, we are comparing the means of groups, right? That's really what we're after, right? And we can see that in our null hypothesis. Go to compare means, one-way analysis of variance. The quantitative number, the variable that you find the mean of, in this case, it's time. It could be blood pressure, it could be blood sugar, whatever, right? The thing that represents a number goes into the dependence list, right? The nominal variable goes into the factor list. Male, well, I wouldn't say male, female, it's only 2. But, group 1, group 2, group 3, ethnicity, hair color, whatever it happens to be, the grouping, the factors, the name variable goes into the factor box. Okay, under options, okay, and then you would calculate your analysis of variance. Okay, so now if you go into options, you can also check off descriptives, which will, in addition to doing the analysis of variance, will give your descriptive statistics, that table with the means and the standard deviations. Rather than, I like doing it before I even do the test, but you could do it with the test if you wanted to. And at this point, if we reject the null hypothesis, if we fail to reject the null hypothesis, our F value is too small and our significance is greater than 0.05 when we get the analysis of variance box up, we stop right there, we're done. Okay, there should be a line under this. Don't go any further unless you're able to reject the null hypothesis. If we're able to reject the null hypothesis, then you can go ahead and you can perform post hoc tests. Go back, analyze, compare means, one-way analysis of variance, and under post hoc, go in there and click off the test that you would like to do. I'd recommend you probably stick with Tukey or Bonferroni for now. Okay. This is a different textbook, you guys. Sometimes we list this as suggested reading. Agresti is an expensive book. If you can find it cheaply, may not be a bad thing to pick up. You may notice I like the tables from that. But a lot of the tables that I use are from Agresti rather than from our textbook. But you have the advantage of having them also since I've posted them. So at any rate, but if you're interested, you might want to check that book out. I'll post some information about it. So at any rate, so it's a good idea maybe to do box plots or display your data graphically, as well as do the descriptive statistics, so you have an understanding of what's going on, and you can confirm that what you get in your post hoc tests makes sense. Okay, so you run your post hoc test, and the post hoc test will then tell you what the likelihood of being wrong if you look at the individual comparisons between the means. Okay, the other way we can compare, when you do your post hoc test, you'll get a significance for each one of the comparisons between each of the means. You can use that to determine which means are different. You could also look for the confidence intervals that are associated with the difference between each mean 1 compared to mean 2 compared to mean 2. And if the confidence intervals exclude 0, don't include 0, then that's evidence that the means are different as well. If the confidence intervals include 0, that means that you're not 95% sure that the difference between the two means are 0, which would mean you can't reject your null hypothesis. Okay, so confidence intervals should not include the 0 if you want to reject the null hypothesis. Okay, and our p-value for the post hoc test, whichever one you choose, should be less than 0.05, or you don't reject the null hypothesis for that combination of means. Again, you only use the post hoc test if the f-test is significant. In other words, if the probability of being wrong, if p-value is significance for the analysis of variance test is less than 5%. Okay, now which one to use? Which one shall we use? Okay, let's read this. Bonferroni method for pre-planned comparisons. Applied to any pre-planned estimable contrast, can be used for any design, cannot be used for data snooping, which means choose the contrast. In other words, don't run your post hoc test before you actually run your analysis of variance. Okay, so Bonferroni is kind of an all-purpose test. Tukey method for all pairwise comparison. Maybe we'll discuss that later on. Dunnett method for treatment versus control contrast, maybe drug tests and so on and so forth. Sue method for multiple comparison for the best treatment among a group of treatments and so on. So really, for our purposes, perhaps we'll stick with Bonferroni for the analyses that we're going to be doing, because it's kind of an all-purpose test. Okay, what does that do for us? That allows us to compare all the different means to one another without increasing our probability of making a type 1 error above 5%. Unlike the t-test, if we use it repeatedly, it would increase our likelihood of making an error if we kept applying it over and over again. Okay, so that's the reason why these post hoc tests are so important. Okay, let me see. Again, this is the idea of the confidence interval. Okay, if it includes 0, if the confidence interval includes 0, you can't reject your null hypothesis. And you can see that here. Here's our significance for group method 1 compared to method 2, 0.751. No, we can't say they're different. Method 1 compared to method 2, 0.024. Well, that we can say with less than 5% chance of being wrong, we can say that the mean for method 1 is different from the mean for method 2. How about method 2 and method 1? Same deal as we did above, same result. How about method 2 and method 3? Oh, that's less than 5%. How about, and this repeats method 3 and method 2. Again, okay, same analysis we did there with the same results, 0.024 and 0.01. Well, what does this really tell us? This tells us that we've demonstrated that method 3 the mean for method 3 is different from the mean for method 1 and different from the mean for method 2. But method 2 and method 1 are not different from one another. Okay, we weren't able to prove that significantly. Which, between me and you, if we go back and look at the box plot, that's kind of intuitively what we would have guessed would happen when we got to the end result here. Anyway, okay. Should we know other types for the test, post hoc test? For our test, no. We were going to stick with Bonferroni. You don't have to worry about that. If you want, we can research. You could research a little bit further on the internet or in the textbook and get a little bit more information about the other types of tests and where you might apply them. If you get enough interest, maybe post questions. If someone posts questions, if I get a couple of questions posted to the discussions board about, gee, can we examine with how these post hoc tests work a little bit and which ones we should use when, maybe we can address that again when we take another look at this later on. Okay, so here's our result for our significance. Here's our confidence intervals. And notice that for the situations where we cannot reject the null hypothesis, minus confidence interval for the difference between these two means for method 1 and method 2, our confidence interval for the difference, in other words, mu1 minus mu2 is equal to 0, our confidence interval is -6 to +10. So 0 is in between these two. Similarly, method 2 to method 1, 0 is between these two. We can't reject the null hypothesis. But if I compare method 3 to method 1, 1.69 to plus 1.69 to +18, 0 is not in our confidence interval. So we can say that the difference between the two means is different than 0. In other words, they're not equal, right? So you can't, notice that works for both of these. So a p-value less than 0.05 here in the significance, and a confidence interval that doesn't have 0 between the upper and lower bound give you the same result. Reject the null hypothesis that the means are equal to one another. Okay, and here's another look at it graphically. This is a reminder of what that box plot looked like when we were working before. And finally, okay, use the F-test to test the null hypothesis that 2 or more groups have identical means. In general, we're looking at more than 2 groups. You probably, if it's only 2 groups, you would have stuck with the t-test. However, we also kind of demonstrated earlier that the t-test, that if you apply the analysis of variance to 2 groups, you get the same result as you would get for the t-test anyway. This is a little premature, so let's skip that. We're going to learn about the chi-square statistic in the next session. We're going to be learning about that, and we got our assumptions. We normally distributed populations. We could cheat on that a little bit if it's large enough sample. Heteroscedasticity or homoscedasticity. The standard deviations are the same. I'm not sure why it's hetero here. Independent samples, right? Independent and random samples from the populations that we're sampling, which is pretty much true for basically all of our tests. So these are our assumptions. Let me check on that heteroscedasticity. Okay, I think it should be homoscedasticity. Said it homoscedasticity before? Is that a typo? Yeah, my goodness. Where is that? That was before this. The assumptions. Where are the assumptions? Should have been pretty early, I think. I don't want to escape without confirming that. I think heteroscedasticity means, was it all the way at the beginning? I don't see it.
Slide 14.
Yeah, a little further down. I don't want this to get away from us without clarifying it. Okay, was this it? Nope. Oh, here we go. Robust homoscedasticity equals standard deviations. I think that should be homoscedasticity. I'll have to check that and maybe correct this slide. Okay, if it's wrong, it should be homoscedasticity. In other words, the same standard deviations, similar standard deviations. Hetero suggests different standard deviations, which would be the wrong thing. And we only use the post hoc test if the F-test is significant. We do not run the post hoc test unless we can justify it by rejecting null hypothesis using the analysis of variance or F-test. Okay, so that's pretty much it for the lecture version of this whole thing. I like this with analysis of variance. I like doing examples and demonstrating it because it's really, when you look at it, it's really such a simple, straightforward thing that once you get to that, it's easier to understand the lecture material than after you see it done than it is to see the lecture material and then not really get to see it done until after you've gone through all the slides and so on. So hopefully that helped a bit. Okay, I want to do one more thing, and then we'll call it a night. And that is there's a data set on here. Let's see which one it is. I think it is smokers. Smokers' income and age. I want to open that up. And I believe that is it's going to have numerical and categorical variables that we will be able to apply this test to. Okay, here we go. Let's take a look at our variable. Our variables have a value which is scalar, which is the number of smokers per 100 population. That might be like kind of a percentage, like 27 smokers per 100, 57, basically a percentage, right? It's a numerical variable, it's a number, okay? And then we have two nominal variables. We have one that has income, and income is a categorical variable. 5 different levels of income. Level 1, maybe this is poorest, next to poorest, middle income, high middle income, and highest income, for instance, whatever it happens to be. 5 levels of income. Or we have age, and in age we have 3 age groups, right? Youngest, middle age, and oldest, let's say, for instance, right? They're just identified by numbers as different age ranges. And we want to compare the proportions of smokers, the number of smokers per 100 population, based on the income. Is the average number of smokers per 100 population different for each income level or for each age group? Okay, so I'm going to give you guys an opportunity to evaluate that. Let's use income level to do this particular problem. There are 5 groups. Let's look at the average number of smokers per 100 population for 5 different income levels. Compare that. What would our null hypothesis be? Our null hypothesis would be the mean for age group 1 is equal to mean for age group 2, is equal to mean for age group 3, is equal to mean for age group 4, is equal to mean for age group 5. By the way, I'm not in love with this idea of number per 100. It's more like a proportion than an actual number, but I don't love it. But we're going to use it anyway for our purposes here. So mu1 equals mu2 is mu3, mu3 is equal to mu4 is equal to mu5 is our null hypothesis. I'm going to ask you to tell me what our alternative hypothesis is and to let me know whether we can reject the null hypothesis and what the results of our if we do, whether or not we can run our post hoc test and what the results of our post hoc tests are. Okay, so first thing I'm going to pause the recording and I'm going to give you guys about 5 minutes to download this and get a little bit ahead of me on actually doing the calculation. I'm only going to give you 5 minutes because we're close to being out of time. And we've resumed recording again. Okay, so you had a chance to kind of play around with this a little bit. Can someone type into the box there, into the chat box, what would be, remember I mentioned our null hypothesis is for income levels. Our null hypothesis is that the mean for income, smokers for income level 1 is equal to the mean for income level 2, equal to 3, equal to 4, equal to 5, right? What is our alternative hypothesis? Someone type that in there for me. Don't be shy. See, I can't tell if you're typing or not because it's not like my iPhone. It's not like my iPhone when my wife has an iPhone also, and when she's texting, oh, they're not equal. Oh, okay, I got an answer there. Okay, they're not equal, right? Well, that's one. Yeah, that's one null hypothesis is that they are not all equal. So I would add an extra word in there and say they are not all equal to one another, right? And because we're not saying that they're not at all equal to one another, but at least two of them are not equal. So one null hypothesis would be that not all of the means of these populations are equal. And another way of saying it would be that uh, the means of at least two of these populations are different. Could be more than two, but at least two are different. So not all of the means are equal, or at least two of the means are equal. Either one of those would be an appropriate null hypothesis. So let me go ahead and do the analysis. Say analyze, compare means, because we are comparing means. That's why you find analysis of variance there. And I'm going to move my numerical variable into the dependence list. That's my scalar variable number of smokers. I'm going to move my factor, my categorical variable, which has 5 groups, into the factor list. And I'm going to ask it to go ahead. Let me just go into contrast here. Nope, that's not what I want. Options. I can ask it to calculate descriptive statistics for me as well. I didn't bother with that before. Maybe I'll just plug that in there now. Okay, I'm going to click OK. You'll see what the difference is when that comes up as well. And here's my output table. There's my analysis of variance. And I'm waiting for it to finish up, I think. Well, I don't see my descriptive statistics. Not sure why it didn't come up for me. But let's take a look at what our result is. So our F statistic, the probability that the F statistic, which is based on the differences between the means between the groups and within the groups, is equal to 0.153, and my p-value is 0.957. Can I reject my null hypothesis that all of the means are equal to one another? What do you guys think? Can I reject my null hypothesis and go ahead and do my? I failed to reject my null hypothesis. What about the my post hoc test? Well, I'm out of business. If I can't reject my null hypothesis, I can't go ahead and do my other tests. Let me try another one here. Compare means. This time, I'm going to try it for age ranges. Whoops, went the wrong way there. Put age ranges into my groups. Let's see if that works out. Okay, let's see. For different age ranges, in other words, mu1, remember the 3 groups there. Mu1 is equal to mu2 is equal to mu3 is my null hypothesis. My alternative hypothesis is not all of the means for all of the groups are equal, or at least 2 of the means are not equal. So it's kind of saying the same thing. Okay, in this case, my F statistic is 51. My probability of being wrong if I reject the null hypothesis is less than 1/10 of 1%. So now I can reject my null hypothesis. I can go back, say analyze, compare means, whoops, one-way analysis of variance, and run my post hoc test this time. And I'm going to pick Bonferroni again and click continue. And I'm going to see which of these that I can say are different from one another. So what I'm looking for here is I'm looking for significances that are less than 5%. This is not less than 5%, so I can't say the mean for age range 1 is not equal to age range 2. No, but I can say age range 1 is different from age range 3. Okay, and age range 2 is also different from age range 3. So I can say that, but I can't say age range So age range 3 is different from the mu for age range 1 and age range 2, but 1 and 2 are not different from one another. So I can say that these two are different, right? But I can't say that 1 and 2 are different from one another. Okay, so my post hoc test allowed me to narrow down which means of which populations I can say are different. But I could only run that test once I confirmed with the analysis of variance that at least two groups were different from one another. Okay, so that's it. So that's where we stand with this. Okay, so hopefully this is relatively understandable to you and you'll feel comfortable with it. Now, coming up is going to be this Wednesday, 2 days from now. We're gonna look at something called contingency tables and chi-square. Okay. Now following that, we have an exam scheduled for the 16th. I guess that's Monday, the 16th. We have an exam set. This exam's going to be online, so technically we won't meet as a class. You'll work on the exam. Maybe what I'll do is I'll stop up here anyway. So if anybody wants a review material or something like that, I can stop by. But we won't have an actual official. We won't introduce any new material that night. I'll post like what time I'll be here and stuff like that. Maybe we'll do the whole period. But I'll post exam 2 on Monday, the 16th. Exam 2 will cover everything we did from exam 1. It'll cover confidence intervals. It'll cover the t-test, the t-test for for single samples, two samples, equal variances, unequal variances. It'll cover the analysis of variance and the post hoc test. I won't include chi-square on it, even though we're gonna start covering that on Wednesday. I won't include chi-square on it. I'll hold off on chi-square until we get to the end of the semester. July 20. The end of the semester is like 3 weeks away. The end of the semester seems funny to say that, right? The end of the semester, the final project or exam, which will be due by. I actually posted earlier. It'll be due by July 25th. And what I'll do is that I'll move the chi-square into that. So instead of analysis of variance, that'll be pushed up before the exam for exam 2. Then chi-square will be pushed down here for after exam 2. So exam 3 will include chi-square and correlation and regression, right? And you'll have a choice of doing a relatively simple, straightforward project where you demonstrate, how you would apply statistics to a real database, right? Or take exam 3 with those two topics, correlation, regression, and chi-square. So you'll have a choice on that. So that's the layout for the rest of the semester. We're already pretty far along the semester here, so please go back. And if you have homework so far, I'll be posting some more homeworks as we go along also. That'll be practice for these topics. But if you have homeworks you haven't taken your extra attempts at, you haven't got your grades up for, and so on and so forth, please go back and do those so you don't get stuck at the end of the semester. The other thing is don't forget about the city program certificate. I need you guys to complete a city program certificate and upload it to Blackboard in the appropriate spot. And occasionally I go through Blackboard and I check them off. You'll see in the grade center that you see a check off if I've acknowledged your city program certificate. And remember at the beginning of the season, the first week I said, you should really do that the first week, while things are not busy before we get piled up with all these other stuff at the end of the semester. Well, the chickens have come home to roost, as they say. So now it's too late, and now you got to do it along with all this other stuff. So don't say I didn't warn you. Okay, but at any rate, please try and get that in before the end of the semester at all. And please try not to wait too long so you don't wind up in a situation that is really tough for you. Okay, are you going to structure the test like last? Yes, pretty much the same as last time. You'll have 2 attempts. You have it online. It'll be open book. You can go, for instance, if I ask you about the assumptions for analysis of variance, you'll be able to go to the PowerPoint or to the PDF file for that PowerPoint, and you'll be able to look it up and so on and so forth. But it may be timed, right? So you'll have 3 hours to do the test, which will be more than enough time. But if you know how to do do the test in SPSS. If you know where to find the assumptions for analysis of variance, where you've seen it, and so on and so forth, you've reviewed the material, you won't waste time going through a lot of material trying to find stuff that you could use for doing other things on the exam. So it's worth studying a bit for the exam, even though it's an open book, even if it just means getting comfortable with the material and where you can find stuff to look it up when you need to. And along with exam two, I'll be posting the databases and uh, 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 the the way that you will become what you would have to submit for the project. Basically, it's you would be getting a database that has many variables and a lot of data in it, and you will be able to choose which variables you want to work with and apply the appropriate statistical test to it and demonstrate a null hypothesis and alternative hypothesis, and also fill in a little bit of information about why you chose that and what you're demonstrating. For instance, you might have your database might include information about influenza vaccination. In other words, whether or not people in the database have gotten a flu shot, and whether or not what ethnic group they might be in, what income group they might be in, whether they have insurance, whether that insurance is whether they are native to their nativity, whether they're born in the United States or not born in it, and so on and so forth. And you may be interested in seeing if whether or not a person is insured or not has an influence on whether or not they are likely to get an influenza vaccine. So you might combine that with a little bit of research where you can flesh out kind of a report, 4 to 7 page report on the association between an influenza vaccine and ethnicity, different ethnic groups or different income groups or insurance status and so on and so forth. Show your descriptive statistics. Show your tell us what your null and alternative hypothesis is. What statistical test you chose to employ, and what the results of that was, and what your discussion and conclusions are about that. Right? Nothing gigantic. You choose just a few variables you want to work with, two or a few variables you want to work with, and put it together in a cohesive report. I'll have a description of what you should include in it, as I've just described. And 4 to 7 pages would be fine. And that means you don't have to take exam three. The reason why I like that is because it gives you an opportunity to really apply these tests the way that you would apply them if you were an actual researcher gathering the data and then being faced with how you're going to analyze it. Okay, now as far as like analysis of variance and correlation regression, there'll be some modest homework assignments on them as well. So it's not like you're going to run off scot-free and not get a chance to practice that a little bit. But on the project, instead of exam three, instead of having to prepare for anything that might come out of that, on the project, you pretty much can choose the direction you go with it. You go with T-test, analysis of variance, chi-square, regression if you want.